Thank you for meeting with me. So I'm coming at MBT kind of from the philosophy perspective,
Good.
and I'm very familiar with your work. I've been following you. I think I came across the London lectures in 2008 or something,
Hmm.
and I've read the book I think twice all the way through, but I go back to it. So I kind of wanted to talk to you to try to ask a few questions that maybe you haven't been asked before, or things that I'm still kind of trying to figure out. I think I've got a really good grasp of your theory, but there's still a couple of little things. So there's a lot of different ways that I could have approached it, but I've kind of boiled it down to four different topics. So I
Okay.
still want to touch on epistemology, metaphysics, the medium of experience. But first, I would like to talk about your experiments because I've recently kind of delved deeper into experiment one.
Hmm.
A friend of mine spoke to me about your experiment one and concerns that came up about those in the
Hmm.
past. And I listened to your audio, which was a response to those concerns. But also, I did my own research, and so the original concern was that you're never going to get an interference pattern on R3 where your screen is. Um, and that is a prediction made by quantum information theory, which is essentially what you're testing. You're testing whether or not the detectors determining the witch path information causes collapse, or whether it needs to be made available to a conscious observer to cause collapse. Quantum information theory seems to say that it doesn't matter if it's made available to a conscious observer, if it's determined by the polarizers or the BBO crystal or the calcite crystal. If it's determined, then it's going to cause collapse. So the concern was that your R3 screen is always going to produce a diffraction pattern. It's never going to produce an interference pattern. So that concerned me because I love experiment one. I've always wanted that experiment done. And I just assumed that your setup was correct and it would be working fine. But when this was brought up to me, I was like, oh no, maybe I should look into this and make sure, see for myself. So I looked at your actual setup and the way you have it. It's a little different than the way it was presented originally, but I think that's just because it has to be that way. And after doing my own research, I've kind of convinced myself now that your experiment is going to succeed, and I'm very excited about it. But I kind of wanted to get your take on uh, the kind of the specifics of how it works, and I can actually bring up a screen share of the setup if you want.
Sure. Why not? If we're going to show this to other people, that would be handy so they would have some idea what we're talking about.
Okay, let me see if I can do that.
No. Okay.
I don't know if that's accurate to the way
Yeah,
you have it
that's
set up now,
pretty
but
accurate. Yeah.
okay.
Except let's see, one change. There is a change in the way it's actually working now, but the change is kind of neutral. It doesn't cause things. Instead of sending a vertical or horizontal polarized signal S, the bottom path, the blue path, it's sending a diagonal polarization, and then the filters, the P, the yellow and the pink, instead of being horizontal and vertical, are anti-diagonal. It's a 90-degree diagonal. And the reason for that was simply the equipment worked better. It was it was not theory driven, but driven by practicality. When we used that, we got better. We got more good data. So that's one change. Let's see. I don't think we're using a calcite crystal anymore. I think we're using some other sort of beam splitter that separates polarity rather than a calcite crystal. But basically, that is the idea. And a few comments about this experiment. If you look at the experiment, if we just look at the one that I briefed in my 2016 talk in Los Angeles, that's where I first presented these experiments, and I have pictures of that. It would be nice to show that picture in contrast, because you'll see there's a lot of things added in order to make the experiment work. I had a very simple experiment where you had photons coming at the slits. Then from the slit, you had a which way detector, and that which way detector would determine what slit it came through, and that which way detection would be recorded. So you had a which way detector on both slits, and that information was recorded or not recorded.
Right.
Now, when you have it that simple, I think it indeed will work exactly the way I say it will work. But what happens is that is a very difficult experiment to do. As you can see, all this complication. We have polarizers, crystals, BBO. We have all kinds of things that were not in my experiment that have been added to it. And when you add, particularly in this case that we're doing here, the polarizers, you add another element to it that then causes the standard quantum physics to come out the way they say. But it's because of the added elements. If you could just do the simple experiment that I have listed, then I think it would work exactly the way I say. But once you add all these things, and the good news is, Chad, is that we're just starting to get data now on this experiment. And I've got a couple of experiments in. When I mean experiments, it is this experiment, but you have to run it a lot of different ways. So this is one way to run it. Another way is to put the absorber further up front, just after it comes through the BBO crystal. Another way is to, do it with and without the polarizers. So there's all kinds of things that you can change here to try to find out what exactly is going on and why. And I'm in the process of doing that now. Last time I talked with Farbod, he said that he wasn't quite getting as good results as he was. So something got bumped, very minute. When you're dealing with light, it's very fast, it's very small, and you have wave, you have wave properties to deal with when you do things like polarizers.
Right.
So it's a different kind of experiment. And I'm now kind of say, well, yeah, but what if this and what if that? And I'm looking at what standard quantum physics says and what I say, and kind of David, who's doing this experiment with me, he's kind of the devil advocate. He's playing the part of the standard quantum physics, and I'm playing the other side. And we kind of going back and arguing and seeing, what happens. And what I found is that if we could just do the simple experiment that I'm talking about, which doesn't have all of these extra things added to it, I think it would work just like I say, just as I say. And I don't know that that's impossible, but it seems to be very difficult. And what I found out is I've gone through the way that standard quantum physics explains these experiments, and I've taken several of the experiments. The first one being the one published in 2000. I think it was finished in 1999, but the publication wasn't until 2000. That was, let's see, it also used, I'm trying to think of the guy's name. Anyway, that escapes me right now, but it was a similar thing. It uses an entangled pair, and then it uses the one path of the tangled pair to develop the which way data, and the other as the particle goes to the screen. It did not have polarizers in it, but in the very end, it did show no interference pattern. okay, but on the screen. But that's a little misleading. And the standard quantum physics, see there, just as we predict, there's no interference pattern. But if you look at, that's one where you do coincidence counting.
Right.
And if you look at the coincidence counting going through the two detectors that determine the which way data, you find out that there is a diffraction pattern produced by each slit. So if you look at that, you say, okay, when I say diffraction, you say diffraction to mean particle. Sometimes people say diffraction to mean interference. So we probably ought to not use the word diffraction, because the interference pattern is also a diffraction pattern. So let's talk about either a wave pattern and a particle pattern, or an interference pattern and a particle pattern.
Okay.
Okay, so that each slit, if you looked at just the photons that went through slit A, they fell into an interference pattern. And if you look at just the particles that went through slit B, they fall into an interference pattern, just as I predicted. The difference is that there's a phase shift. There's a phase shift of pi between them. So when one's up, the other's down. And when you put the two of them together on the screen, you get nothing. Okay, because everywhere there's an up on one, there's a down on the other. They're waves that are phase shifted pi. That's 180 degrees.
Right.
So
a
they're
friend.
directly out of phase. So when you think about it, A and B both did produce interference patterns, just like I said they would. But the result of the slit is the combination of those two, which it always is. What you get on the screen is always the combination of where the electron went through, A slit, and where the electron, the photon, goes through in B slit. So it's always that way. So at the slits, my theory was correct. That was what you did get an interference pattern produced by each slit, but it just so happens they're pi out of phase, and that's why you don't get an interference pattern at the screen. So you see, I would kind of count that a win. The pattern you get from each slit is indeed as I said. Now, why do you get this phase shift? Well, there's lots of different reasons, and in my estimation, they all have some problems. The one that is held up by most of the quantum theorists, I've seen at least 3 different reasons for the pi shift, which when there's 3 different reasons, that tells you that they all really don't agree. 3 different reasons. So it just comes out in the math that there's a minus sign someplace, and that minus sign causes the phase shift. But I know how physics works and how physicists work, and they tend to modify the equations to suit the answer. That's just, they look at it and say, oh, well, look, this should have been a minus sign here, and that explains it. And they has a justification of why that was the case. But so I don't really believe any of those. So I think, in a sense, I'm verified there, because we do get interference patterns from each slit, and they just happen to be out of phase. Now, this experiment that we're doing here has the same problem. If you look at what goes through each slit, you get interference patterns. If you look at the pattern on the screen, you get the two interference patterns out of phase with each other. So it looks like it's a particle pattern. It's just no humps, because every hump was met with a dip exactly about the same size. So it's that sort of thing that's going on. And that's because the reason that you have these phase differences in my experiment is because of the polarizers. That's what causes the phase shift. So I pulled the polarizers out, and I got a beautiful interference pattern. And anyway, so I'm just in the process of, of working these kinds of things out. David and I are. So hopefully in a month or so, when we've kind of exhausted what we can learn from this experiment, I'll be publishing all of that.
Right. So one thing, I'll share my screen again. And if you just look at this portion where you had the polarizers originally, what I was looking into, so if you didn't, so here you have the horizontal at A and the vertical at B, and then you've got the
Right.
diagonal right before the screen. So from what I was looking at, if you don't have the diagonal there, you get exactly what you were talking about. You get the particle pattern, and that's from the fringe interference pattern and the anti-fringe interference pattern overlaid on top of each other.
Yeah, or another way to say that is that you have two sources. One's, for one slit, it's horizontal, the other slit is vertical, and those two can't interact. Those two waves are orthogonal to each other. Neither one can have a vector, on the other. So they just can't interact. You're taking two sources of light that cannot interact and produce an interference pattern because they have to interact with each other to produce an interference pattern, and they're orthogonal to each other. So that's basically just an optics thing, not really a quantum physics thing. So that's
Right.
why that doesn't work. So you put the P, the green one there, which
Yeah.
then takes both of them, will produce a component for the the horizontal will have a component in the diagonal direction, and the vertical will have a component in the diagonal direction. Now you have something that can. But let's say that those polarizers cause some phase shifting, because we have to look at an actual wave. An actual wave is like, think of it as like a sine wave, right? You get a sine wave. It has a positive peak and then a negative peak, and then a positive peak and a negative peak. So I don't know. Let's see. Let me get this thing I have up here out of my way so I can see my own finger here. You have a vector goes up and down and up and down. So it's going up and down as the trig function goes from 1 to 0 to -1 to 0 to +1 and so on. That's what the sine wave is doing. Well, those are going through those things. Well, now when it gets to that, so you got a horizontal and you've got a vertical, and do we know that they're in phase when they both hit this diagonal? Is one of those at the up part of its cycle in its way, in the waveform, the wave cycle, or was it at the down part of its cycle? Well, if they're opposite, then you've got that same problem again. You'll get them out of phase. So even though you're supposed to get a pattern that way, and you do, if they both, the vertical and the horizontal both have exactly the right phase in them. One's hits this peak this way as it hits the horizontal peak that way, and then the components will all line up. But if those components don't line up, then you'll get those two that'll be just opposite each other. So then, even with that setup, you may not get an interference pattern. That would be possible. It just depends on the details of how each wave, what part of its phase it is. So now we're talking about things that happen at half a wavelength. A wave shifted just a little bit one way or another. Now, if you're real careful, I suspect that it will work most of the time if you're sure that your light is precisely coherent. But by the time you run it through something like a BBO crystal, then kind of all bets are off. That changes. You're running it through a crystal. The speed of light inside that crystal is slower. So how thick's the crystal, and what does that do to the phase? So if you just have a coherent light and the polarizers, you'll probably always get an interference pattern with the horizontal and vertical will probably be lined up just perfectly together. But when you stick crystals and other things into the mix, calcite things, you're changing things. And I don't know that that's necessarily accounted for as it should be. And then it would be possible to look at that setup you just showed me and not get, an interference pattern. There's other details we have to look at. And that was what I started off saying. if you just look at the picture that I put on my 2016, say, here's the experiment, that's so simple and pristine because it's theory. It's not the practicalities that you have to go through to actually do the experiment. And that theory, I think, will work exactly as I say. But once you add all the complications that you need in order to actually make a measurement of the which way data, now suddenly you've got a handful of variables that you didn't have before. And that kind of changes things. And you've got things going on like that phase difference between them.
Right.
I have another reason why there's a phase difference. Pi has nothing to do with a minus sign anywhere. And that, I think, the reason that there's a pi phase shift there is that the detectors in that experiment, there was a D1 and D2 were the detectors that
You're talking about
detected those,
delayed
the
choice
Sully,
quantum eraser
yeah,
from
right, delayed quantum eraser, Sully et al.
Okay.
Kim, Sully, Kim, Wu, and
Right.
4 others. It was D2 and D1 were the 2 detectors that detected particles that were then erased. By the way, they had fancy little mirrors and things that erased the which way data. The particles, you had the which way data erased. And those erased data went to 1 and 2.
There you go.
Yeah. So it's D1 and D2 after the particles were erased, right? So now the way they set up this experiment is that every so often, you get something out of that pump and it's very regular. So you regularly get a photon that comes there, goes through this process, and goes into one of these 4 detectors, D1, 2, 3, and 4. And that process is constant. It's just, like you could think that every second a particle comes out, And if you look at the count, in D1 and D2, you realize that count, the sum of D1 and D2, has to be a constant. The number of counts you get in each one of those when you run through the coincidence counter, you're getting them at a constant rate. So D1 and D2, sum of D1 and D2, have a constant rate. Well, if they have a constant rate, then each one produces its own interference pattern. But if they were in phase, then you'd have to go a whole lot of counts when you're at the peak and not many counts when you're at the bottom. You couldn't have them coming regularly. You couldn't have consistent counts like they do. So because they have consistent counts, then you have to have a phase shift of pi between those two so that the result produces data evenly, consistently, just like the counts. So that's another way of looking at that problem that doesn't have a minus sign that somehow got changed to suit the problem, or any of the other things that they say are the problems. None of those actually make sense either. This one actually makes sense. The physics would tell you that you have to get a result that is uniform in the data rate, because the incoming data rate is uniform. The outgoing data rate has to be uniform. Can't change that. And the only way to do that is if there's a pi phase shift between them. So in any case, you see, my simple experiment has not yet been done, and I'm thinking it's very hard to do. In order to do these experiments, you need all kinds of other things. You need BBOs and prisms and beam splitters and all this other stuff. These beam splitters sometimes, they transmit, sometimes they reflect. But when they transmit, there's phase shifts. Every time you reflect, I think there's a pi phase shift. And when you transmit, maybe there's no phase. And there's other things that happen. You get a pi over 2 phase shift. So it becomes a very complicated mishmash of things going on. And the fact that if you look at all the particles that go into D2, which is where the data was erased and all the particles going into D1, look at those separately and look at all the particles on the screen that went through, let's say, D1, you'll get an interference pattern. And you look at all the particles on the screen that went through D2, you'll get an interference pattern, just like I said you would. But because they have to be pi out of phase, because of the way the experiment has been set up, then you look at the screen and, oh, you get a particle pattern because the two out of phase interference patterns make a particle pattern. So that's kind of what's going on and where we are. And I'm trying to squeeze as much information out of this experiment as I can. But I'm afraid it's not going to be as clear as what I would hope it would be. But when I do my other experiments, the experiment 3 and 5 or whatever, I got a couple of other ones that are rather dramatic, and they're more dramatic than this one. This one was just to try to understand what was going on there. What was the difference between what I'm saying and what the physicists were saying? You know, why do we get this different answer? So I wanted to do this experiment so I could manipulate the details of the experiment to try to figure out really what was going on. And we're doing that. We're doing that now. And so far, what I'm finding is if you look at the individual slits, you get just what I predicted. And if you take those two individual slits and put them together, those patterns together at a screen, you get what they predict. So, you know, that's the way it comes out. Now you'd think the pattern that goes through a slit, okay, here's the pattern. The particles that go through the slit fall in this pattern, you know, an interference pattern. The particles that go through that put themselves in an interference pattern. So you would think that the answer would be, well, they both produce interference patterns, but they sum to nothing, no interference pattern. So that's
Right.
where we are. It's still a little confused. I think they would claim that they were right. At the screen, there certainly was no interference pattern, but not because there was no interference. There was interference in both slits, just as I said. They get no interference pattern because of the mechanism, the way in which they had to make the experiment work. That's why they're getting this. And it may turn out to be that is necessary. It may be that in order to measure that which way data, you have to do things to it that will always cause a pi phase shift at the end. That you'll somehow have to use polarizers or beam splitters or, you know, other things. And you'll always be using these particles that are entangled. See, I don't have any entangled particles in my thing. I just have particles, and you measure the which way data. But if you
Right.
do these other devices, because of the way you have to use those other devices, you may always get that pi phase shift. So in which case, you know, we're both right in a sense. I'm right at what goes through each slit. They're right at what you finally get at the at the screen.
Are you aware of when I was looking into this, I found an experiment also by Scully done in 1991. They call it the SEW experiment. So it was Scully, Englert, and Walther. But they actually used they did something that's similar to what you're trying to do, and it doesn't use entangled pairs and polarizers. Um, they actually use a cesium atom, and they send it through a double slit. Well, first they energize it with a laser beam after the slits, and then they send it over. I forget the name. It's some type of a cavity that will detect which slit it came through by absorbing a photon from the cesium atom. Have you heard about this?
No, I've not seen that.
Um, so they actually have what it can do is they can detect which slit it came through with the cavity that it passes over, and then they can actually erase the information by having the photon that gets sent into one of the two cavities be absorbed by a photon absorbing wall that's in between them.
Mm-hmm.
And so what happens is when they do that, when it hits the back slide, they still get an interference pattern, even though the witch path information was detected, it was just erased before it hit the back slide. And an interesting thing about this experiment is they also did it where they did a delayed choice, where they erase the witch path information after it hit the backslide. And in that case, you get the particle pattern, which was interesting. So I don't know, I might have to send you that paper if you want to look it over, but
Yeah, well, that makes sense. That's the way it should work, I think.
right.
I think that's pretty much in agreement with me.
Right. Yeah. One of the things about the Kim et al. Delayed choice quantum eraser experiment is a lot of people make it seem like it suggests that there's a retrocausality happening.
It's not the case.
Right. And so yeah, I would like you to talk about that because it seems like there's never any retrocausality.
No.
Things are affecting things in the past, right?
No, no, that's what's going on there. It appears as if there's retrocausality because you change something, you decide whether to erase or not erase the which way data after the particle has already impacted the screen. So as far as what's on the screen, that experiment's already over. And now you decide whether you're going to erase or not erase, the which way data. And if you decide to erase it, then you get an interference pattern. And if you decide, not to erase it, you get a particle pattern. And how is it that you can do something after the experiment's over that changes the result of the experiment? That's kind of the problem. And it sounds like retrocausality. You've gone back and changed the results of the experiment afterwards, after the experiment was done. Well, the way it works is that, let me put it another way. The problem here in thinking is that there are particles, that this is a material reality and there are material particles. And when those material particles do whatever they do, well, that's the way it is. And, that can't be changed. Well, the way the world really works is there are no particles. There's only probabilities. So you might want to call those things not particles, but potential particles, protoparticles. It's not, you see, and there are no particles. That was the whole point of the double slit experiment is, they decided that the only way to make logic sense out of the experiment is if there are no particles. Particles don't exist. There's only probability. And those probabilities remain just probabilities, which means the particle is just potential particle until the measurement's made. And that's what requires, a human to make the measurement, or maybe you could train a dog to make the measurement. Just some consciousness need the data. Okay, so if you think of that particle and those particles and what they did on that screen, until the measurement's made, somebody looks at the screen. Those are just protoparticles, quasi-particles, or however you want to say it. Probability of a particle being somewhere. Now, when you decide later that you're going to erase the which way data, okay, now the probability is that you'll find those particles in an interference pattern. So you do the erasing or not erasing before you look at the results on the screen. That's the key. See, these experiments are all run, they collect all the data, then they start looking at the coincidence counter and sorting everything out. Then they find out what went where. So the answer to that is no, we don't go backwards in time, but you have to realize that particles really don't exist. They only exist in probability until the measurement's made. When the measurement is made, they look at the data, and that data says, okay, when the measurement is finally made, when you look at the screen data, say, where is that screen data? Well, now the experiment is all over. You know, all the particles have already been counted. All the times have been recorded. It's all done at that point. And because there was no which way data, then you're going to get an interference pattern. That's the way, when you look at the screen data, that's what you'll find it, because that's what happened, 10 milliseconds or 10 nanoseconds after it hit the screen, then either got erased or didn't get erased. So that's the answer to that. It's that there are no particles. There's just probability. So what's on that screen, even though that screen should already have particles on it, remember, they're not particles, they're just probabilities. And those probabilities change depending on what happens, whether the which way data gets erased or not. Those probabilities change. So, which means what's on the screen changes, because it's just probability. So you can't change particles. If you got physical particle there, then you can't say, well, the physical particles somehow change. You know, that's retrocausality. But if you really don't have any particles there, you just have a potential for particles to be somewhere. And that doesn't get sorted out until after the which way data is either erased or not erased. Then that probability ripens, becomes a fact, and that's what you see on the screen. So that's the explanation for it. It's not a retrocausality thing at all. It just seems that way because materialists believe in particles, and that when particles hit a screen, by God, they're going to stay wherever they are when they hit there. You know, that's a materialist viewpoint. But if you say, well, when probability gets to the screen, it's not yet, all the calculations aren't done yet as to what those probabilities are. And
Right.
now, if you look at the screen first, if somebody was looking at that screen as the particle hit it, if somebody was sitting there at that screen, say, there's a particle. Now, that particle would have to stay there. Doesn't matter what happened. See, that's my other experiments, my later experiments. This is what I do. I put an observer looking at that screen to see the instant of where it hits. And then I can predict whether it gets erased or not. Because if it happens to fall in a particle pattern, then I say, oh, it didn't get erased. The which way data will be collected on that one. Now here comes the particle, and I can say, well, when it gets to this point, it's going to reflect, not transmit at that beam splitter, because it's going to have to say that particle was collected, you know, there at number 3 or number 4. So those are my later experiments. I put an observer right there at the screen, and then that observer can predict what's going to happen at the mechanism that does the erasing or doesn't erase. It'll say, oh, now that entangled particle is going to transmit through that and go through the eraser process because this landed inside of an interference pattern. And what I do is I run the experiment just by itself for, I don't know, a long time. So I got a real strong pattern. So I know exactly what it is. And then I look at the statistics and I find if a particle lands here, what's the probability that that's part of a interference pattern or part of a particle pattern? You see? So I have it all mapped out ahead of time and what the probabilities are. So if you land right in the middle of a peak, well, you're going to have a probability of 1 that's interference. If you get a high count there. If a particle lands right between peaks, well, that's going to be a space where there are no peaks. So if you map that out, you know exactly where the peaks and dips are going to be. And then you can say where it lands. Here's the particle. Where does it land? Oh, that one landed right on a peak. Okay. So now you start saying, well, I'll count that as a peak particle. Now it might not be. There are some particles that just kind of make a fuzz at the bottom. There's some noise or some other things like that. But the statistics will follow you. So if you do that, you'll be able to predict, say at 70% accuracy, what happens when it gets to that beam splitter. Does it reflect or does it transmit? Well, that's impossible.
Mhm.
See, because that's just a photon getting to a beam splitter, and we know that's random.
Mhm.
That's random by nature. How can I predict that? The only way that can be predicted as if there is some awareness in the system that knows what the right answer is ahead of time. You see? Bingo. That's what makes that experiment significant, because it not only makes a good point for particles being probability distributions, which that to me is obvious. There's only one good explanation for how that could ever happen, and that's that this is a virtual reality. How else could particles be probability distributions? It's a probability based virtual reality. There is no other answer for that. That's the only rational answer. So we got that already. And then on top of that, now we have consciousness as the computer. There's some evidence for consciousness as a computer, because something smart enough to know what's going to happen next decides whether that's going to reflect or not reflect. And I can tell you what that's going to be, but it hasn't happened yet. So now there's something manipulating this experiment, and it's something with intelligence and a brain, because it's not just randomly doing stuff like a machine. It's purposefully doing things, manipulating that. It's not random at all. The system, it appears to be random, but that's how the system is able to do its magic behind the scenes. So that's what those other two experiments are like. So I do one of them like that, where the experimenter can predict whether a photon will transmit or reflect, which is just by physics just totally impossible. And then the other one, it's the prediction of how a particle will be emitted from a radioactive source.
Okay.
You have a radioactive source, and it emits particles randomly in any direction. And then you have this big counter that detects radiation, a hemisphere on either side. And if it goes through this hemisphere, that's you're going to erase the data. If it goes through this hemisphere, you're not going to erase the which way data. So you let that change, and then it's the same thing. You look and see where the particle lands. Oh, it landed, in a place that is where a dip occurs. Then that's not part of a whatever. So then you can make a prediction. Oh, that radioactive particle, which is now 20 nanoseconds down the line, is going to decide to do, it's going to come out on the right side instead of the left side, because that makes a difference on whether you erase the which way data or don't erase the which way data. So now
Right.
it's the same thing. You do something that is just absolutely physically impossible. You can predict which side a particle is going to come out of a nucleus that's decaying, which is random. So it's impossible. And it gets you to, it's exactly the same experiment, but it's just done in a different way with a different thing. And it says, well, in order to do that, there must be something intelligent that is aware of the situation that changes what we thought was random isn't really random, or doesn't have to be random. It could be random, but if the system needs it not to be random to prevent a discrepancy in the rule set, then the system will change that. So anyway, those are those two experiments, and I think they will be even more impactful than the first one. The first one is not going to end up, oh, I'm right, they're wrong, or oh, they're right, I'm wrong. It's going to end up in this thing that, well, as far as what the particles do when they leave each slit is exactly what I said they do. But the way they end up on the screen is exactly what they said would happen. So then we can have an argument about what all that means, but it's not going to be clear. In order to measure that which way data, so far it looks like you have to throw a lot of extra variables in there. You can't just, like in my theoretical model, says, oh, you just have a detector. You just detect the which way data. You see, it's pure and easy, and it's it's no problem. It's just a theoretical thing you do. You just do it. And I think is probably never going to happen. It's always going to be complex. But now, I may be wrong there. There may be some clever scientist here someday who'll say, come up with a clever way of doing it without introducing the other issues into the experiment, like pi phase changes and things like that.
Right. The SEW experiment I was mentioning it seems like it kind of does that.
I'll have to look at that. Yeah. Send me a link to that when you get a chance, Chad.
Okay. So we're almost an hour in. I got one more question I wanted to ask about the experiments, and then I want to move on. So another criticism that has been put forward is that if your experiment one worked the way that you suggested, it would allow for faster than light communication. And I at first thought that that's not correct, because people often think that entangled pairs can allow for faster than light communication, but that's not right, because you don't know ahead of time which way it's random, whether it's going to be. But I was looking at your experiment, and I was looking at it if it worked out the way you said, and it seemed like you actually would be able to have faster than light communication. You just have someone on one planet looking at the screen and seeing if it's going from interference pattern to particle pattern. And then you have someone on another planet switching the absorber on and off, and they can send Morse codes. And it looks like the person looking at the screen could get the information. It's not random, it's intentional. So what do you say about that?
Yeah, I thought about that some too. And I think you probably, I think it has two aspects to it. One, I think it does allow you to transmit data faster than light speed, transfer information. Now, information's non-physical, so you can't make anything physical go faster than light speed. That's Einstein. But information doesn't necessarily get caught in that trap, because information's not physical. Okay,
Right.
It's different. Now, you can't transfer physical data that fast, yes, but again, information is a different sort of thing. So that's a possibility, but I think it would be so totally unwieldy to make any kind of meaningful communication. If your communication can be made in 3 or 4 bits, and no more, like you got, okay, 2 ones and a 0, now what are you going to say? Well, you're just not going to say much. And it's not that easy to do these experiments. It's not that easy to set this up. And there may be some other constraints on it that we haven't thought yet. It may be some decay time on that, before the system declares that the experiment's over and it no longer works. The system's in charge. And what I mean by that is, okay, let's say you do a whole bunch of simple double slit experiments, and you get outputs, and you don't look at either one. You don't know what they are. So you've done them all such that there was no which way data, or you've done some of them so there's no which way data, and some of them that there was which way data. Say, so if you want, you can give somebody the screen data, and you keep the which way data, and then you erase the which way data, and now their screen data should show a interference pattern. Okay. Well, the idea is that there can be an infinite amount of time between those two actions. I don't know that the system will allow that.
Right.
The system can make up their own, their own rules other than the rule set that it has to work with. It can just say that there's, a decay time. And that's not that's only good for, I don't know, for a day, for a year, for a decade, for 10 nanoseconds, who knows? There may be some decay time that would be imposed on that, but nobody's ever looked at that or done it or seen what the other variables might be. So there may be some other, if it got to be that communicating faster than light speed was a problem somehow, then the system could do something that made that not work, like a lifetime, something that would decay, or just the practicality of it, I think would make it very difficult to turn it into Morse code. That would be such a cumbersome way of trying to communicate.
Yeah.
That I don't know that it would, I don't know, maybe later science that we don't understand now might make it more efficient process. But yeah, I believe it does say that you can make a communication. That depends the distance. Okay, look at that delayed eraser. When they finally, that photon gets to D1 or D2, which means it gets erased, or D3 or D4, which means it doesn't get erased, that's 10 nanoseconds later. And then the result changes because nobody's ever looked at the result.
Mhm.
All right, so that's 10 nanoseconds. So we've done it already for 10 nanoseconds. Okay, we've communicated information. 10 seconds, 10 centimeter or 10 nanoseconds later. And the communication was, I'd say, faster than light speed. It was instantaneous. As soon as that happened, it's done. Okay, so now if you can do it for 10 nanoseconds, you ought to be able to do it for 10 years. It's the same setup.
Mhm.
So we've seen it with 10 nanoseconds, but we haven't seen it, for much more than that. And so I think that is a possibility, yes. But whether it ever turns out to be a practical possibility or whether the system allows it to be a practical possibility, those would be unknowns that we just don't know yet. But yeah, that's interesting that at least there's a possibility there that someday we might have faster than light speed if you could
Mhm.
somehow harness that. But it's not exactly a kind of technology that you can imagine that it would be. You know, it would be really hard to get enough bits there that you could have anything more than a grunt and a gesture. It'd be very, very simple communications.
At least for now, yeah.
Yeah, at least for now.